Welcome to session 5. The topic we'll be discussing here is continuation to medium access control. So we'll be discussing some more medium access techniques. So these are the techniques we'll be discussing here. Reservation TDMA, reservation time division multiple access, and we'll be discussing another concept called MACA, multiple access with collision avoidance, using which the problem of hidden terminal and exposed terminal can be overcome. And then we'll be discussing the concept polling, and also we'll be discussing another concept called ISMA, inhibit sense multiple access technique. And finally we'll be discussing CDMA, that is code division multiple access technique, using some special codes how the shared medium can be accessed, where the medium will not be shared either based on frequency or based on time, but it uses a special code for sharing the wireless media. So this is what we'll be discussing in this particular uh, session. The learning objective of this session is, after going through this session, the learner will be able to understand the working methodology of reservation TDMA, and they will be able to understand the working methodology of MACA, and also they will be knowing like how MACA helps in avoiding the hidden and exposed terminal problems. And the learner will be understanding the concept of polling, and also they will be knowing like how any bit sense multiple access technique works, and also they will have a clear understanding about CDMA, code division multiple access, how code division multiple access helps in accessing the shared media by multiple users at the same time by using some special codes, and using this code how the data can be encoded and how it gets decoded. Okay. So these are the objectives. So let us start with reservation TDMA. So reservation TDMA, it is also one of the reservation schemes. Previously we have discussed few reservation schemes like that. This is also one such reservation scheme. Here what happens in the sense, every frame consists of n mini slots and x data slots. So if you see this diagram, this is one frame. This is frame 1. Okay. Sorry, not this. So the frame 1, this is frame this is frame 1. Okay. So up to here, this is frame 1. Okay. So if you take each frame consists of n mini slots and n into and x data slots. Okay. So this is called as mini slots, and these are the data slots. All these are data slots. Okay. So this is nothing but data slots up to from here to here. This is data slot. How many data slots are there? X data slots. This x is given as n into k. This x is given as n into k. Okay. So basically every frame here contains n mini slots and x data slots, where x can be given as x equal to n into k. So every station has its own mini slot, and it can reserve up to k data slots. It can reserve up to k data slot. So k represents like each station maximum how many slots they can reserve. That is what this k specifies. Each station maximum how many slots they can reserve, that is what given by k. Okay. So the basically the working concept is, the mini slots are fixed for every user. The mini slots are fixed for every user. Like for example, the first mini slot may be for user A, for mobile station A, the second mini slot for mobile station B, the third mini slot for mobile station C. Like that, each mobile slot is basically fixed for a particular user. So if user A want data slots, then he should reserve during his mini slot, and also he should reserve how many data slots he want. If user A want only one data slot, then he can say one. If he want two data slot, he can say I want two data slots. Like that he can say. Maximum how much data slots he can reserve, in the sense he can reserve up to k data slots. He can reserve up to k data slots. So this diagram, it is an example where n is equal to 6 and k is equal to 2. Okay, where n represents the number of users. So here what is n? N represents the number of user and k represents the maximum slot each user can reserve. So we know that there will be, each frame will have n mini slots and n into k data slots. So here the number of mini slots is 6. Why there are 6 mini slots? Because our value of n is 6. So maximum this can be used by 6 users for reserving the data slot. Okay. So here what happens, in the sense, first user is reserving only one slot. Maximum he can reserve two slots because the value of k is 2, but he is reserving only one slot. So the second slot of the first user will be empty. Second slot of the first user will be empty, which I am representing using a cross symbol. Similarly, the second user is reserving both the slot. So his both the slots are reserved. That is, he is going to use this is both the slots. Third user is not reserving anything. Third user is not reserving anything. So both his slots are empty. Both the slots, so he can reserve up to k slots. So here k value is 2. So both the two slots are empty. Fourth user is reserving only one slot. Okay, so fourth user is reserving. So the first slot is occupied by him, and the first slot will be occupied by him during that slot, and the second slot is empty. Fifth user has reserved both the slots. So he is going to use both the slots, and the sixth user has also reserved both the slots. He is also going to use both the slots. Okay. So this is how the concept of reservation TDMA works. And wherever there are free slots, other stations, those who have not reserved the time slot, but if they want to use now, then the other station can use the free slots in a round robin fashion. So whatever the free slots, it can be used by other stations, and by that time when they are accessing, they should follow the round robin pattern. So this is the working methodology of reservation TDMA. So here the time slot, here a frame consists of n mini slots and x data slot, where n represents the number of users and x will be equal to n into k, where n is the number of users and k is the maximum slot that can be reserved. So during the mini slot, every user will have their fixed mini slot. So during their mini slot, they have to reserve the data slots. So they can reserve up to maximum k data slots. So if somebody has not reserved their data slot, then that will be empty slot. And empty slots can be used by other stations in a round robin fashion. So that is the concept of reservation TDMA. Fine. Next we will be discussing about MACA, multiple access with collision avoidance. Already we have discussed that we need a special MAC for wireless networks because we cannot borrow the same MAC protocol which is used in the wired network to wireless network, because the wireless network cannot sense the collision which is happening at the receiver end. So the collision detection basically will fail. As collision detection uh, fails, this protocol cannot be used. The same wired protocol cannot be used in wireless networks. And also there are other issues like hidden and exposed terminal problems and near and far terminal problems. So we need a special MAC for wireless networks. So one such proposal is MACA, multiple access with collision avoidance. So, so basically it uses two special symbols. Basically it uses two special signals. One is RTS, the other one is CTS. RTS stands for request to send. RTS stands for request to send. So whenever a sender want to communicate with a receiver, he will not directly send the data. Yeah, it's not that just he will sense the carrier. If the carrier is free, he will send the data. No, it is not like that. Rather, before before the actual communication, sender will first send an RTS to the receiver. Sender will send an RTS to a receiver, requesting the receiver that I want to communicate with you for certain amount of time. So this RTS packet will include the sender IP address. It will also include the receiver's IP address, and also it will include the time duration during which the communication will exist. If receiver is free at that time, and if the receiver is ready to communicate with that particular sender, then the receiver will respond with the CTS. The receiver is free, and if the receiver is ready to communicate, then the receiver will respond with a CTS. CTS stands for clear to send. CTS stands for clear to send. So now there is a agreement between the sender and the receiver. Now the sender and the receiver can start communicating between each other. So this is how this MACA concept works. Okay. So if the sender will first send an RTS, and if the receiver is ready for communication, then the receiver will send back a CTS, and then they will communicate. Okay, this RTS and CTS are special signals, and these signal packet include the sender address, the receiver's IP address, the sender's IP address, and also it includes the time duration the communication will exist. Now let us try to understand like how this can be used to solve the problem of hidden and exposed terminal problems. So first let us see how it can be used to solve the hidden terminal problem. So we know the hidden terminal problem. The hidden terminal problem, what it says in the sense, A can reach B, but it cannot reach C. C can reach B, but it cannot reach A. And B can reach both A and C. Now, if A sends some data to B, A senses the carrier is free, so it sends some data to B. At the same time, if C also want to send, C checks the carrier is free, so C also sends the data. But now there will be a collision at B. This collision cannot be identified by A because C is hidden for A. Okay, so this problem is called as hidden terminal problem. This problem is called as hidden terminal problem. Okay. Now let us see how this hidden terminal problem can be overcome by using this technique. So now what happens in the sense, before A communicates to B, A will actually send an RTS to B. A will actually send an RTS to B. So RTS is request to send. So it includes A's IP address, B's IP address, and also duration of the communication. This RTS will be received by B, but it will not be received by C because C is not in the detection range of A. Okay, or C cannot detect packets that were sent by the A because C is not in the range of A. But after certain time, but B will receive this RTS, and after certain time, B will reply back with the CTS. B will reply back with the CTS, accepting its request. Again, this CTS will include the A's IP address, B's IP address, and also how much time this communication will exist. Now, this CTS packet will go to A and also it will go to C. Okay, but by seeing this CTS packet, A will understand that B has accepted its communication, and they both will start communicating. And they both will start communicating. But C will also understand that. But C will also understand that now B is communicating with A. C will also understand that now B is communicating with A, so it will defer its communication. So it will defer its communication. That is, C will not immediately send any RTS or any request to B stating that I want to talk with you. So this is how the hidden terminal problem is overcome by using this particular algorithm, which is MACA, multiple access collision avoidance technique. Now let us see how this technique can be used to overcome the problem of exposed terminal. So first we know what is exposed terminal. With exposed terminal problem, what happens in the sense, there is a mobile station B which is located close to C. The mobile station B will be close to C. As it is close to C, as mobile station B is close to C, whatever A sends, B will drain A's energy. B will drain A's energy and C cannot receive A's communication. B will drain A's energy and C cannot receive A's communication. So this is the problem with exposed terminal. Okay. Now let us see like how exposed terminal problem can be rectified by using MACA. So now MACA, what it does in the sense, so now B wants to communicate with A. Okay, B want to say if B, uh, so sorry, I defined exposed terminal wrongly. So exposed terminal means B wants to communicate with A. B is communicating with A. B is communicating with A. Now C want to communicate with somebody else. Maybe it is D. And C senses the medium, but C finds that the medium is busy because B is communicating with A. So thinking that the medium is busy, C will defer its communication. But actually C need not defer its communication. But actually C need not defer its communication because C's communication with D, it is not going to affect any way. It is not going to affect any way the communication of B with A. So C basically need not defer its communication. So this problem is called as C is unnecessarily now deferring the communication. So there is a wastage of time. So this problem is called as exposed terminal problem. This problem happens because B is exposed to C. This problem happens because B is exposed to C. Now let us discuss how this problem can be uh, rectified. So, so, so how it is done in the sense, first, first B will send an RTS to A. First B will send an RTS to A stating that I want to communicate with you, which includes sender's IP address, that is B's IP address, and receiver's IP address, that is A's IP address, and the duration of communication. This RTS will be received by A and also it will be received by C. But this RTS is intended for A. This RTS is intended for A. After some times, A will return back, A will send back a CTS accepting B's request. This CTS will not be received by C. This CTS will not be received by C, but C has received the RTS. So C understands that B now want to communicate with A and it is going to communicate with A. So B will understand that B is not communicating uh, with any other, with C or with somebody else. So it knows that B is communicating with A. So now C need not wait to communicate with D. C can communicate with D. Okay. So C knows that if it communicates with D, that is no way going to affect B's communication with A. So C will not now differ. It will just directly communicate with D. So this is how the exposed terminal problem is rectified by using MACA technique. That is by using multiple access collision avoidance technique. Okay. So this is the working methodology of MACA, multiple access collision avoidance. The next medium access protocol that we'll be discussing is polling. So polling basically means one station is going to check whether if anybody wants to talk, communicate. Then it will connect with that station and it will communicate. So if one terminal can be heard by all others, then this central terminal can poll all other terminals according to a certain scheme. So that concept is called as polling. So one such example is random address polling. In random address polling, the base station uh, signals the readiness to all mobile terminals. That is, whenever the base station is ready to receive data from the mobile terminals, it will send a signal to all the mobile terminals stating that now I am ready for communication. If anybody want to communicate with me, now you can communicate with me. Like that, the base station will send a signal to all the mobile terminals. The, the terminals that are ready to send will transmit at random. The terminals, that is the mobile stations that are ready to send, will send data randomly. That is, they will not follow any order or they will not follow any protocol for synchronization. Just they will transmit the data. Okay, and base station chooses one address for polling from the list of all random numbers. So see this random number. This is a random number. Okay, that is all the terminals will send a random number. So basically, this random number uh, represents the address of that particular terminal. Here, terminals that are ready to send, in the sense they will communicate randomly, but along with that they will also send a random number. Along with that they will also send a random number. Using the random number, using that particular random number, uh, the address of a terminal can be identified. Address of the particular mobile station can be identified. Okay, if two terminals were selecting the same random number, then it will result in a collision. If two terminals select the same random number, then it will result a collision. So the concept here is base station will first send a signal stating that I am ready for communication, and whenever base station is ready for the communication, the terminals will all send a random number to the base station. Okay, they will generate a random number and they will send to the base station. And if two base stations, if two terminals create a same random number, then that will result in a collision. Now using this random number, the mobile station will communicate with that particular terminal. So the mobile station choose one of the address from the list of random numbers for communicating. Okay, like that it will choose one by one and then it will communication. Then it will communicate with that particular station, and then the data will be transmitted between the mobile station and the base station, like that. Okay, and the base station also acknowledges the correct reception of the packet from that particular mobile station, and then it will continue to poll the next terminal. So so this is the working principle of polling. So So initially the base station will signal that I am ready for communication. Once it is ready for the communication, the terminal should send a random number. That is, it should send a unique random number which will identify that particular terminal. If more than one terminal generates a same random number, then it will create a collision. Now the base station will get a list of random numbers where each random number can be connected to the IP address of one of the terminals, mobile terminals. Now it will start polling one by one terminal based on the random number, and the communication happens between the terminal and the mobile station. And whenever the mobile station receives a packet successfully, it will also send the acknowledgement. So this cycle will again repeat after polling all terminals of the list. It is once all terminals where polling is done, then again base station will send a signal for ready for communication. Then again all terminals will send and create a random number and it will send. So like this, this particular pattern will repeat. So this concept is called as polling. The next kind of medium access technique that we'll be discussing is ISMA. ISMA stands for Inhibit Sense Multiple Access Technique. Here the current state of the medium is signaled through a busy tone. The current state of the medium is signaled through a busy tone or an idle tone. Okay, it will be either signaled by a busy tone or an idle tone, which acts as an indicator. So, if the current state of the medium is signaled through a busy tone, then it means the medium is currently busy. It means that the medium is currently busy, and nobody else can use the medium. Somebody else is already using the medium. That is the meaning. If the if it is idle, then it means that currently the medium is idle, and if somebody wants, they can use the medium. Okay. So base station signals on the downlink. So base station will signal this information through the downlink. The communication from the base station to the mobile station is called as downlink. So through the downlink, the base station will communicate to all the mobile station through this signal whether the medium is free or not. If the medium is free, it will send an idle signal. If the medium is not free, it will send a busy signal. So like that, basically it will communicates its whatever the state of the medium to all the mobile station. Okay. If the medium is busy, then the mobile terminal will not send any packet to the base station, because the mobile terminals know that the medium is busy and now it cannot communicate, because already uh, somebody else is communicating, or the or base station is doing some other task, so the medium is not free. So if the medium is not free, if the medium is busy, then the mobile station will not send any information. If the medium is free, if the medium is free, that is if the busy tone stops, once the busy tone stops, the mobile station will access the medium. Okay. Once the busy tone stops, the mobile terminals will access the medium. And if there is any collisions, if there is any collisions, the uh, the base station will notify that collision, either will notify that collision through the busy tone. Whenever there is a collision, the base station will notify that collision through a busy tone. And if the data is received successfully, then also the base station will notify through acknowledgement. Okay. So this is how inhibit sense multiple access technique works. That is the current state of the medium will be signaled by a busy tone or idle tone by the base station through the downlink, whether the medium is free or not. If the medium is busy, the mobile terminals will not send any information. If the medium is free, that is if the busy tone stops or if there is an idle tone, then the mobile station will start sending the information. If there is a collision, then once again the base station will create a busy tone. If the data is received successfully, then the base station will also send an acknowledgement, which is an information to the mobile station that the data has been received successfully. So, so this is how the technique inhibit sense multiple access works. And so media access is not basically coordinated within this approach. Only coordination is whether the busy tone or the idle tone. There is no other further coordination. This diagram basically explains like how it works. The base station will send a signal which is either busy tone or an idle tone. If it is busy tone, the mobile station will not communicate. If it is idle tone, then the mobile station can communicate. And whenever the medium is not busy, the mobile station will send uh, information to the base station, and if there is a collision, again the mobile station will create a busy tone. Okay. This is the working concept of ISMA. So the next medium access technique that we'll be discussing is CDMA, collision detection multiple access. So this is very different from all other techniques because here the medium is not shared either based on frequency or based on time, but it is shared based on some special code. The medium is shared based on some special codes, and using this code multiple users can communicate at the same time through the medium. So different users should identify their own codes, and the codes should be orthogonal to each other. Okay, that is, the code should not be similar. So using the code, the information will be decoded and it will be sent. And using the code, the information will be encoded and it will be sent. And the receiver again should use the same code to decode the information to understand the actual communication. So here all terminals send on the same frequency and also at the same time, and can use the whole bandwidth for the and can use the whole bandwidth of the transmission channel. That is, everybody can use the uh, entire bandwidth of the channel. Each sender has a unique random number. Each sender has a unique random number, which is the code, And the sender, what he will do is, the sender will XOR the signal with this random number. The sender, whatever the data he want to transmit, that data will be XORed with this particular random number. The receiver can tune into the signal if it knows that random number. So that random number is nothing but the code. Okay, so this XOR operation is nothing but the encoding operation. Here this XOR is nothing but the encoding operation. Okay, so after encoding, the sender will send the data, and receiver, what he will do is, after receiving this information, he will decode it using the same random number. Using the same random number, the receiver will decode. So the receiver should know using which random number the sender has encoded. So that information the receiver should be knowing. So this is the basic. Let us try to understand this with an example. Also, before that, let us see what are its advantages and disadvantages. So the disadvantage of this particular technique, CDMA, is it requires a high complexity receiver. Receiver cannot just listen into the medium and start receiving if there is a signal. So the receiver should know the code and he should decode. So all these, so the receiver, the complexity of the receiver is high when compared to other means of other multiple access techniques. And also the signal should received by the receiver with a good strength. If the strength of the signal is low when it is getting received by the receiver, then the receiver cannot decode the signal properly. The receiver cannot decode the signal properly. The advantage of this technique is all terminals can use the same frequency. All terminals can use the same frequency. No planning is needed. No need to divide the frequency or no need to divide in space of time. And the code space is also huge when compared to frequency space. The frequency space is limited, but the number of codes available is not limited. Okay. And the other advantage is the interferences are not coded. Okay, you only code the data. If there is a noise or interference, it won't be coded. So if something is not coded, then you can ignore that as a noise. So that is another advantage. And forward error correction and encryption can be easily integrated. So these are the advantages and disadvantages of CDMA techniques. Let us understand how CDMA works with an example. So say the sender wants to send a data 1. So the data he wants to send is 1, and this is the key or the code. Here this is the key he is using. What key? 0 1 0 0 1 1, 0 1 0 0 1 1. Okay. Now before applying the coding, we make some little modifications. Wherever there is a 0, we represent the 0 with -1. Wherever there is a 1, we will represent it as +1. All zeros will be represented as -1 and all ones will be represented as +1s. Okay. So if the now the sender wants to send the signal, this one data he want to send. Okay. So what he will do is, this process he will do AD into AK. AD is the data and AK is the key. So AD into AK is what? So AD is 1. So this 0, instead of 0 we use -1. So it is basically AD is 1. Okay. AK is actually 0 0, sorry, 0 1 0 0 1 1. But all zeros we are converting to -1. So it is -1 comma +1. Okay, then next -1 comma -1 comma +1 comma +1. Okay. So now you multiply this. So now when you multiply, you will get the same thing because you are multiplying with 1. So -1 +1 -1 -1 +1 +1. So this is the actual signal that sender is going to broadcast. Okay. Now there is another sender B. Say B want to send the data 0. Okay. And B uses this thing. And the key used by B is 110101. And again here also we represent all 0 as -1 and all 1 as +1. And before sending, B will perform this encoding, which is BD into BK. So BD is 0, but 0 we represent as -1. Okay, so -1 into what is that? It is +1. So first there are two ones. So that will be represented as +1, and then there is a 0 that will be represented as -1, and then there is a 1 that will be represented as +1, and then there is a 0 that will be represented as -1, and then there is a 1 that will be represented as +1. Okay. So +1 +1 -1 +1 -1 +1. So this is multiplied with -1. So what will happen? All the signs will change. So this will become -1 -1 +1 -1 +1 -1. So finally the sender B will send this particular data. Okay. So this is the encoded information that the sender will be sending. Now before sending, now both are sending at the same time. A is sending this and B is sending this, and they are sending at the same time using the same channel. So when you send the same signal at the same time, when multiple signals are sent at the same time by different users, they will superimpose with each other. They will superimpose with each other. So here let us neglect the noise, all those things. So if it gets superimposed, what will happen? -1 plus -1 will become -2. Okay, so this -2 comes. +1 -1, it becomes 0. Again -1 plus 1 becomes 0. Again -1 plus -1, it becomes -2. Again 1 plus 1 becomes 2. Again +1 -1, it becomes 0. So this is the superimposed signal that is getting sent. This superimposed signal will be transmitted. Okay. And whenever the receiver receives, receiver will receive the superimposed signal. So assume that receiver A is receiving. A is receiving, the receiver corresponding to A signal is receiving the superimposed signal. But that is not what A sent. A sent this. So now how A will rectify that? But A sent 1. So how the receiver will decode? So for decoding, again the receiver should use the same key. Again the receiver should use the same key. Okay. So here the information is what it is, -2. So let me do here. This is the information, -2 0 0 -2 plus 2 0. So with that you will multiply A's key. So A's key is what? -1, +1, -1, -1, +1 and +1. Okay. So that is A's key. So if you multiply this with A's key, what we will get? If you multiply this with this superimposed signal with A's key, finally what we'll get is -2 into -1 is +2. Okay, +2. 0 into -1 is 0. 0 into -1 is 0. -2 into -1 is again +2. 2 into 1 is again 2. 0 into 1 is 0. So basically we got 3 2's. Add all the 3 2's. It is 6. It is 6. It is 6 which is greater than 0. Okay, so you can consider that it as 1. So this is how the decoding is done. And the original data send is also 1. Okay. So now the data is successfully decoded. And this is the digital information. So you can send either 1 or 0, nothing else, right? Now let us see how B will decode. So B also receive the superimposed signal. So B, what it will do, B will apply its key. B will apply its key. What is B's key? What is B's key? B's key is, so here now you have to apply B's key. So B's key is what? 1 1. So B's key is +1, +1, -1, +1, -1 and +1. So this is B's key. So if you apply B's key to this data, what you will get? 1 into -2 is -2. Again 0 into this -2 into 1 is -2. 0 into +1 is 0. Again 0 into -1 is 0. Again -2 into +1 is -2. Okay. Again +2 into -1 is -2. Again 0 into +1 is 0. So basically we got 3 -2. If you add all the 3 -2, what you will get is -6. So -6 which is less than 0. So we have to consider the data as 0. So if you see, the actual data that is sent by B is also 0. So 0 is now received here successfully, right? So this is how CDMA works. So like that, any number of user can use the same channel with the same frequency at the same time they can send. All the signals will be superimposed and it will be sent, and the receiver will extract the actual data by using his key. The only thing is the keys that were chosen by different senders should be orthogonal to each other. Only that should be ensured. So otherwise this technique will work fairly well. Now let us see how CDMA works through these diagrams. So this is the data which A wants to send. So A wants to send 1 0 1. So here 1 is represented using a low pulse, 1 is represented using a low pulse, and 0 is represented using a high pulse. Okay, you can see 1 is represented with a low pulse and 0 is represented with a high pulse. And let us say this is the key. This is the key. This is the key. So what is key? So key is this is the key sequence 0 1 0 1 0 0 1. Right? So first what should we do? The data will be XORed with the key. The data will be XORed with the key. Okay. So in the previous case we have changed to 0 to -1, 1 to +1, but here we are not doing that. Here in the timing diagram, let us see how it works. Here we are directly XORing the data and the key. So data is all 1 here. Up to here it is 1. Okay. So that will be XORed with the key at different time. So 1 or 0 is 1, 1 or 1 XOR 0 is 1, 1 XOR 1 is 0, 1 XOR 0 is 1, 1 XOR 1 is 0, 1 XOR 0 is 1, 1 XOR 0 is 1, Okay, so this is how you got the C. Like this here, like this, all these here, all these things are 0. Okay, and this is the key, and this is the key followed for this particular transmission. 1 0 0 0 1 0, 1 0 0 1 0. So 0 or 1 is 1, 0 or 0 is 0, XOR, I mean XOR, 0 XOR 0 is 0, 0 XOR 0 is 0, and 0 XOR 1 is 1, 0 XOR 0 is 0. So like that it continues. Okay, fine. So this is how the signal is XORed. Okay, so after XORing, this is the data you get. Okay, fine. Now how the signal will be transmitted? The signal will be transmitted like this. Here we are representing 1 with a low pulse and 0 with a high pulse. So whenever there is a 1, we are using low pulse, and whenever there is a 0, we are using high pulse. So this is 1 low pulse, this is 0 high pulse. Here continuously there are 3 ones, so 3 low pulse. Okay, here continuously there are 3 zeros, so 3 high pulse, again low pulse, like this. So basically this is how the data is getting transmitted. So this is the continuation of uh, the previous thing. So this is what signal A is. Okay, similarly let us see another signal B. Similarly, so this is the signal generated for A, data A. So data A is encoded like this. By using a key, it is XOR and it is encoded like this. Similarly, let us see for another data B. So this is signal A, which is continued from the previous figure. This is the signal A, which is a continuation from the previous figure. That is this. Okay, and in the next figure, this, both are basically this and that in the previous figure are same. Okay, now let us see for another data B. So B wants to send this data 100. Okay, so B's data is what? 1. So 1 is represented with a low pulse and followed by 2 zeros, which is represented with a high pulse. Now this is the key followed by B. 0 0 1 1 0. Okay. Again for the next data it is using 101 0 0 0. Again it is using 0 1 0 1 1. Okay. So this is the key which is basically followed by B. Now you XOR as usual. 1 XOR 0 is 1, 1 XOR 0 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0, 1 XOR 1 is 0, 1 XOR 0 is 1. Like that XOR is done for everywhere. Okay. Then finally this is the signal for B we are getting. So all ones are represented using a low pulse and all zeros are represented using the high pulse. So this is the signal for B and this is the signal for A. So both A and B are sending at the same time. So these two signals should be superimposed. So when you superimpose, what you get is, when you superimpose, what you finally what signal that we are going to get is, this is what we are getting. So this is low pulse and low pulse. So actually this is low pulse is 1 and high pulse is 0. But basically here what you are doing, you are actually adding, we are actually we are actually adding two low pulse. Okay, so two low pulse. So basically it is a low pulse. Basically it is a low pulse, right? So this is also a low pulse and this is also a low pulse. So this is why here it is a low pulse. Okay, but in the next case what happens is, this is a high pulse and this is a low pulse. Okay, so you are adding a low pulse and a high pulse. Okay, for better understanding, let us consider in signal A and signal B, all low pulse let us consider as -1 and all high pulse let us consider as +1. Okay, so here also all low pulse let us assume as -1 and all high pulse let us consider as +1. This is for our understanding of the working, how we got this AS plus BS like this. Okay, so this signal A and B should be superimposed. So when we are superimposing, we are getting like this. How we got? So for this, let us have this assumption: all low pulse is represented with -1 and all high pulse is represented with +1 in signal A and B. Okay, so here during the first time period you can see this is -1 for signal A, and for B also it is -1. So if you add this both -1 plus -1, what you get is -2, so that the line is low. Here you can see the gap between these two lines, it is less, but here you can see the gap is more. So this is -2. Okay, so -1 will be somewhere here, -1 will be somewhere here. Okay, so what I'm trying to say in a sense, just for our understanding, we can consider this point as -1. Okay, and this is 0, sorry, this is -2, and this is 0. Okay, similarly there will be something here, so there will be something here, this can be considered as +1, and this can be, and the top one can be considered as +2. Okay, that is, this particular thing can be considered as +2. Okay, fine. So with this we can understand this plot. So here you can see it is both low, both, I mean it is in the shorter pulse. Okay, it is in the downward pulse. So it is -1 and -1, when you add -2, so you are getting here. The second case, it is +1 and -1. So +1 and -1 is 0, so that we are getting this line here. Okay, here we are getting here because it is +1, and here it is +1, here it is -1. But here when it comes coming for the third pulse, it is again -1 and -1, so you are getting -2. Okay, the fourth case, it is +1, here also A is also, it is +1, and B is also +1, so it is +2, so you are getting here. Okay, the +2, right? Okay, in the fifth pulse, it is, for A it is -1, for B it is +1, so it becomes 0, so it is here. Okay, the sixth pulse, for A it is -1, for B also it is -1, so it is -2. So like that the plot continues. So this is what we get for AS plus BS. Okay, now this is what it is getting transmitted. Now let us see how A and B decode this information using the key. Okay, so this is the, so let us see how A decodes it first. Let us see how A decodes it first. So A, so this is the actual data sent by the A, right? 101, 1 is represented with the low pulse and 0 is represented with the high pulse. Now this is what A received finally, the superimposed signal, and this is AK. This is the key used by A. This is the key that is used by A. Okay, so again here, whatever the key that is used by A, it is represented uh, in this format. Okay, that is -1 and +1. So here also with the key, what you can understand is this part is 0, this is 0, this is +1, and this is -1. Okay, so if the line is here, then it is +1, if it is here, it is -1, otherwise it is 0, but there will not be any 0, so it will be switching between +1 and -1. With respect to AS and BS, it is between -1, it is between -2 and +2. Okay, so now let us see how it what do you call, how it regenerates that particular signal. Okay, so what, so here you can see this is +1, this is +1, and this is for for AK, it is +1. Now +1 will be multiplied with this. Okay, this is a, so this is what, this is, this is actually -2. Okay, this is actually in B's case, in AS plus B, this is -2, this point is 0, and this point is +2. Okay, so here what happens, minus 2 is multiplied with plus 1, so what you get is resultant is minus 2. So it is, the line is here. Okay, the second case, the second case 0 is multiplied with minus 1, so anything you multiply with 0 it is 0. So the line you are getting in the zeroth point. Okay, the third case, as plus bs is minus 2 and ak is plus 1. So again minus 2 into plus 1 is minus 2. Okay, so it is here. And in the fourth case, as plus bs is plus 2 and ak is minus 1. So plus 2 minus 1 is again minus 2. Okay, and in the fifth case, the fifth case in the fifth case it is, in the fifth case, as plus bs is as plus bs is 0 and this is plus 1. Okay, so plus 1 into 0 is 0, so you are getting in 0. Okay, the sixth case it is minus 2 into plus 1, so it is minus 2, so it's here. Okay, and in the next case it is minus 2 into minus 2, which is plus 4. Okay, minus 2 into minus 2, minus 2, so this, sorry, minus 2 into minus 1, which is plus 2, minus 2 into minus 1, which is plus 2, so we are getting here. So here you can see this is 0 for our understanding. This is, this point you can take as 0, this you can take as minus 2, and this you can take it as plus 2. Okay, so you are getting this in plus 2. Similarly, next case it is plus 2 and plus 1. So plus 2 into plus 1 is 2. Okay, so you are getting here. The next case it is 0 into plus 1, so it is 0, you are getting here. So like this it continues, like this it continues, right? So finally this is what the signal you got. Finally this is what the signal uh, we are getting. Okay, so if you convert this signal to an, what you call, if you convert this signal to an analog signal, if you convert this signal to an analog signal, the integrated output will be something like this. Okay, so for the first data, for the first data you will get an output something like this. Okay, which means uh, it is actually, the signal is uh, starting at high and it is then going down. Okay, so okay, so this is what the, for the first case you're getting. And for the second case what you are getting is, you are getting something like this. And for the third case you are getting like this. Okay, and the comparator will convert this to 1 and this to 0 and again this to 1. Okay. Okay, so basically what you can understand from here in the sense, see this particular point. So here you can see all signals are in this area, in this area. So which we can see as a lower, what do you call? It is a, it is represented in the lower part. Okay, but here if you see all signals are uh, in the higher domain. Again here it is in the lower domain. Okay, so this is what you can infer. So whenever it is a lower domain, we will say it is 1, because that is our original data. In our original data also, we are representing 1 in the lower domain and 0 in the higher domain. Okay, so here also you can see whenever this actual information is in the in the lower domain, we will say it's 1. When it is in the higher domain, it is 0. So this is how the integrator produces this kind of signal, and from that the comparator is creating 1, 0 and 1. So like this the data is retrieved in A. Okay, similarly the data can also be retrieved in the similar fashion in B. So you can go through this, walk through this, and you can work out. But if you use a wrong key, if you use a wrong key, this won't work. Similarly, for B also, you can check out and it is generating the same data, whatever the data generated, whatever the data transmitted, the the same data it's able to generate here also. Okay, but this cannot work if the key is wrong. Okay, if the key is wrong, then ultimately it will not create the proper output. So here everything depends on the key. So there should be a proper synchronization of key between the sender and the receiver. So so let us walk through this uh, B also. Let us walk through the B also. So you can see here, this is B's data. B wants to transmit 100, and this is what AS plus BS is, and this is the key used by B. This is the key used by B. So when you perform AS plus BS into BK, this is what you are getting. Okay, and when it is converted to data signals, this is what you are getting. So this is same as the original data. So that is how it is recovered. But when you use a wrong key, when you use a wrong key here if you are not using the correct key, then then finally when you perform AS plus BS into K, the correct data is not getting recovered. Okay, instead of recovering the correct information, you are recovering the wrong information, right? So this is how the CSMA technique works. The next technique that we'll be discussing is SAMA. So SAMA stands for Spread Aloha Multiple Access. SAMA stands for Spread Aloha Multiple Access. CDMA needs a complex receivers to be able to receive different senders with individual codes at the same time. Okay. So Spread Aloha Multiple Access, it uses basically spread spectrum with only single code, which is otherwise called as chipping sequence, for spreading all senders, for spreading all sender uh, accessing the medium according to Aloha. Okay, so let us see how the spread Aloha multiple access technique works. Let us assume that this is the data which A and B wants to transmit at the same time. A wants to transmit 101 and B wants to transmit 101, and they are sending at the same time, using the narrow band, using the narrow band, and there is a collision. You can see here there is a collision. So the A's packet is colliding with the A's 1 is colliding with B0. Okay, similarly, so this is similarly B's 0, A's 0 is colliding with B's 1, and A's 1 is colliding with B's 1. Okay, so to avoid this collision, so instead of sending this signal in the narrow band, the signal can also be sended with a high power in a short duration of time. Instead of sending the signal like this, the signal can be sended with a high power in a short duration of time. Okay, then it can be sent like this. So A is sending first 1, then B is sending 0, then again A is sending 0. Okay, then again B is sending 1, then again A is sending 1, and then again B is sending 1. So if you convert the signal in this format with high power, if you transmit, it can be transmitted without collision, but then we need a high power to send this. Okay. But instead what we can do, for because we need a high power, but always you may not have a high power for transmitting. So instead we can use a chipping sequence. We can use a chipping sequence to transmit the data. So this is the chipping sequence that will be followed. The chipping sequence that will be followed is 110101. This is an example. Okay. So whenever there is a one, okay, uh, whenever there is a one, the signal will be transmitted in the upper side. Okay, whenever there is a 0, the signal will be transmitted downwards. Okay, so initially A wants to send 1. Okay, so this 1, so this is as usual the previous case. All 1 we are representing as +1, all zeros we are representing as -1. So above this line, all these things represents +1, and below this line all this represents minus 1. Okay, so this is the basic idea. Above this one everything represents plus 1, and below this thing everything represents uh, minus 1. Okay, so whenever if the sender wants to send 1, then this whenever the sender wants to transmit a data, it will be multiplied with this chipping sequence. So here initially sender want to send 1. Okay, so multiply this 1 with the chipping sequence. So what is the chipping sequence? Chipping sequence is 110101. Okay, double one will represent as plus 1. Plus 1, uh, plus 1, comma 0 is minus 1, again plus 1, again 0 is minus 1, again plus 1. Okay, so when you multiply 1 with this plus 1 with this, what you get is same thing. You will get plus 1 plus 1 minus 1 plus 1 minus 1 plus 1. Okay, so this one is spreaded and it is transmitted like this. First there is a plus 1, okay, that is this, and then there is another plus 1, that is this, then there is a minus 1, that is this, which is the blue color, and then there is a plus 1, which is this, and again there is a minus 1, which is this, and again there is a plus 1. So this is how this first one is transmitted. Okay, this is how this first one is transmitted. Next, sender A wants to transmit a 0. So when you want to transmit 0, so now he want to transmit 0. Okay, so 0 will be, so 0 is nothing but what? So 0 is nothing but minus 1. So 0 will be represented as minus 1. So now minus 1 will be multiplied with this particular chipping sequence. So now you multiply minus 1 with this chipping sequence. So minus 1 into plus 1 is minus 1. So this, just the sign will change. So it will become minus 1 plus 1 minus 1 plus 1 minus 1. Okay, so what we are getting, minus 1 plus 1, okay, minus 1 plus 1 minus 1 plus 1. Okay, like that it transmits. Again it sends 1. Similarly the case for B also. So initially B wants to transmit 0. So B wants to transmit 0 means it is same, minus 1 plus 1, like that the data gets transmitted. So here the challenge is in identifying the correct chipping sequence. But here we send the signal by spreading it based on the chipping sequence. So now the signal is also spreaded. So you don't need much power to send the signal. Each signal you need less power, and it is spreaded over time, and it is getting transmitted. Right? So this is how the concept of SAMA, that is the spread aloha multiple access technique, works. So let us